in the last lecture of week 10, I will summarize what we have learnt in week 10 and do some practice problems. So, week 10 lecture 5 will be summary of week 10 and practice problems. So, what did we learn in week 10? In week 10 we learnt about the crystal structures of elements and simple compounds. Okay. So, we first looked at closed packed structures and voids, okay, and we understood where the octahedral and tetrahedral voids come in closed packed structures. Okay. And then we looked at the crystal structure of elements. Then we saw crystal structures of binary compounds. We looked at several binary compounds and we saw their crystal structures. Then I looked at two interesting ternary compounds. Okay, these are perovskites and spinels, and we saw their structures. And then finally, I discussed the concept of space filling polyhedra alloys, and we looked at Hume-Rowe 3 rules. Okay. So, now I will go to a couple of practice questions. I mean, in this week I want to emphasize that there aren't really too many, I mean, most of it is descriptive. So, so the questions will be mainly related to things like coordination number or calculations of distances, okay, but most of the other concepts are fairly descriptive. Okay. So, this is a question: what is the coordination number of gallium and nitrogen in word-site GAN, okay, and what are the number of gallium atoms closest to any gallium atom? Okay. Now, the word-site crystal structure is essentially two interpenetrating HCPs. So you can look at it as two interpenetrating HCPs, okay, or you can alternatively you can look at it as HCP plus tetrahedral voids. Okay. And you can already see, the moment you say half of tetrahedral voids, you immediately realize what the coordination number is. Okay. So, in this you can think of the gallium atom as occupying the tetrahedral voids, not half, it is just, I will just say tetrahedral voids. Okay. So now what will this structure look like? So if you have an HCP, okay, then let me show the sulfide ions in red. And I am deliberately not showing them touching each other. Okay. And now this is the hexagonal cell, and then in an HCP, okay, you have an additional sulfide and located here. Okay. Okay, so these are the locations of the sulfurs, and the gallium we can choose the locations. So, we can choose whichever tetrahedral voids we want them to occupy, but definitely there is a tetrahedral void in the right here, okay, which so I will put a gallium right here, and this will be directly above this sulfide ion, okay, and actually it will, this goes somewhere here, it comes out. Okay, so that is the location of the tetrahedral void. Okay, so it comes out right in between these three. goes out. So, the gallium is located right in this void, okay, which is actually in the coordination polyhedron is basically it is closest to these 4. So, that is the tetrahedron of coordination. Okay. So, now what is the coordination number of gallium and nitrogen? Okay. So, clearly gallium is 4 coordinated, okay, and since these are 2 interpenetrating HCPs, okay, then the gallium will also form an HCP. So, the gallium will also form an HCP. In this case, it will be there will also be gallium atoms here, and then it will and the whole will be here and here, and this HCP will extend. Okay. You will additionally you will also have some gallium atoms that are right above these. Okay. So, you will also have not this one. You will also have gallium atoms that are here, okay. And so you can see the now I am showing the coordination polyhedra for this nitrogen atom, okay, and that is also 4. So, nitrogen also has coordination number of 4. Now, the next question is what is the number of gallium atoms closest to any gallium atom? Okay. Now, this can be answered very easily. So, since gallium forms HCP, okay, the answer is just 12 gallium atoms closest to any gallium atom. Okay. So, if you look and similarly for nitrogen also. So, if you look at any gallium atom, okay, there will be 4 nitrogens that are closest to it. Okay. So, the coordination on number 4 relates to the 4 nitrogen atoms that are closest to it. Okay. And the nitrogen atom has 4 gallium atoms that are closest to it. But if you look at gallium, what are the gallium atoms that are close to it? Then the answer is 12. Okay. So, there are 12 gallium atoms closest to any given gallium atom. Okay. The next practice question is suppose you assume that gallium nitride forms a perfect word side structure and that gallium and nitrogen atoms are in contact with each other. What should be the ratio of the size of nitrogen atom with respect to gallium atom? Okay. So this question can be answered in a few different ways, but let me mention a few things. So, the perfect word side structure means gallium or I will start with nitrogen forms a perfect HCP, and so does gallium. So, the individual gallium and nitrogen, okay, let me write it separately. So, gallium, the individual gallium and nitrogens, they form perfect HCP. Okay. And what should be the ratio of size of nitrogen atom with respect to gallium atom? Okay. So, again you can do this very easily. So let us say we take the nitrogen as a larger atom. Okay. So, if perfect HCP, okay, then gallium should occupy tetrahedral voids. Okay. So, if nitrogen forms a perfect HCP, then the gallium should occupy the tetrahedral voids. Okay. And so therefore radius of gallium should be equal to radius of tetrahedral voids. Okay, this is the radius of the tetrahedral void if gallium and nitrogen are in contact. Okay, so, if they are perfectly touching each other, then the radius of the gallium should exactly be equal to the radius of the tetrahedral void. Okay. So, now the radius of the tetrahedral void in gallium, okay, this in HCP is equal to the radius of tetra or the in terms of divided by the lattice parameter A in HCP is equal to radius of tetrahedral void in CCP. Okay. And we also have seen, okay, this turns out to be two by 4. This is in the case of CCP. Okay. And if I take R tetrahedral void divided by R of the larger atoms, okay, so that becomes root 3 minus root 2 divided by root 2. Okay, because the radius of nitrogen, okay, the larger this is the radius of the larger species. So, R equal to A root 2 by 4, okay, and this is equal to 0.22, about 0.225. Okay. So, what you would expect, so ideally you would want radius of gallium divided by radius of nitrogen should be equal to 0.225. Okay. If the nitrogen forms a perfect HCP and the gallium also forms a perfect HCP, and both of them form a perfect word side structure. Now, of course, this ratio is not exactly satisfied, but it turns out that for gallium nitride, okay, the C by A ratio is very close to 1.62, okay, which is very close to perfect ratio. C by A ratio for HCP. So, for an ideal HCP, the C by A ratio is about 1.63 and this is about 1.62, which is very close to that. Okay. And I took the liberty of using the tetrahedral void in the cubic closed pact, okay, to estimate this, okay, but you can also do this for the hexagonal closed pact and you will get exactly the same answer. So, we can just use the HCP structure and locate the tetrahedral void. In this case, the geometry is slightly more involved. So, just to illustrate, you have the hexagonal closed pact structure. Okay, this is the unit cell. And the tetrahedral void is located right here. Okay, and you can now in a HCP additionally you also have an atom here. So, let me show all these atoms in blue, and you have an atom here, and the tetrahedral void is directly above or below, whichever way you want to show this, okay, this atom. And so you can determine this radius of tetrahedral void, okay, by geometric analysis of this void, and you will get exactly the same ratio. Okay. So, with this I will conclude this lecture, and I will also conclude week 10 of this course. And as I had mentioned earlier, that in this week we sort of saw how all that we learnt about symmetry, packing, crystal structures, okay, all that is used to describe structures of real materials, okay, and how all the language that we learnt in the previous 9 weeks, okay, we put it to use in describing the structures of several materials. And as I said, a lot of the material is very descriptive. So, so I do not expect you to memorize too many things, okay, but at least some basic concepts of this of these structures of solids you should have. Okay. So, thank you.